In section 7.1, we're talking about producing sound, how we produce sound and stuff. And there's this age-old argument, if a tree falls in the forest, does anybody hear it? And a scientist might say, yeah, for sure. If a tree falls in the forest and nobody's there to hear it, does it still make a sound? A scientist would say, yeah, because the sound is just vibrations in air. Maybe a physicist, you could say, would say that. A philosopher or maybe a biologist might say, no, there's no sound until the auditory nerve is stimulated. Who knows? But here's something that we can say. Here's how sound waves are produced. So this is going to be a speaker cone. If you know what a speaker cone looks like, if I've got these big floor speakers at my house, and if I take the front of those off, the kind of, fuzzy stuff on the front so you can see the actual speaker cone. This is what it would look like from the side. And what happens when a speaker cone is making a sound, it actually moves forwards and backwards. And as that speaker cone moves forwards or outwards, what it's doing is it's collecting together all these little air molecules. Okay, so here's a whole bunch of little air molecules. You can't see them, but they're there. You can kind of picture them like a bunch of marbles, like a broom sweeping up a bunch of marbles or something. As the speaker cone moves forwards this way, it kind of gathers together a bunch of these air molecules. Those air molecules now are moving in this direction. They're going to keep moving in that direction. There's going to be a bunch of collisions and stuff. When the speaker cone though moves back to its original kind of rest position, what we've got here then is a whole bunch of these little air molecules that are all kind of traveling this way. They're colliding and sending other ones that way. But those air molecules are all kind of moving outwards. The speaker cone is going to move forwards again, and it's going to collect a bunch more of them together. So what's happening here is the speaker cone is moving forwards and backwards and forwards and backwards. And what it's doing is it's collecting together air molecules. And where the air molecules are kind of tightly packed together, that's like a compression. In here where the air molecules are kind of far apart, we get a rarefaction. But the wave, this disturbance, is all moving out this way. So what we're going to get is we're going to get air that looks something like this. So again, you can imagine kind of like your speaker is over here somewhere. This could be a voice or your music or whatever, but something is making sound. And what we're getting is a whole bunch of these compressions and rarefactions, and they're all moving out this way. And somewhere here I put it, so here's a little picture of the ear. And again, you can picture your speakers off to the left. These the waves, these compressions and rarefactions, this is like longitudinal waves, are moving towards your ear. And somewhere in here there's an eardrum. It's somewhere off the picture, but imagine there's the eardrum. And as this highly compressed air reaches your eardrum, it's going to push your eardrum kind of in this way. And then when you get this much lower than normal, this rarefied air, as that reaches your eardrum, it's going to let your eardrum go out this way. And so what happens is your eardrum, just like the speaker, your eardrum kind of wiggles back and forth, and that is what you perceive as sound. So what you get is this high pressure air and low pressure air and high pressure air and low pressure air. And that difference between high pressure and low pressure is what we can graph that as like a sound wave, or a sine curve. But what that is that your eardrum or your brain's perception of high pressure air, low pressure air, high pressure air, low pressure air, that's what makes sound. That's what we hear. Sometimes people think, it's only the high pressure that we hear, that's loud, and everything else is quiet or something. And it's not. It's the difference between high and low pressure. It kind of takes this full cycle for you to hear a sound. If it's just high pressure, that just is what plugs your ears. If you're going up a mountain or down into a valley or something like that, you feel that your ear plugs. High pressure or low pressure on its own kind of plugs your ear, but the difference between high pressure and low pressure, that's what you perceive as sound. The pitch of a sound is determined by frequency. So if you have like a low frequency, so you can kind of see like the long wavelength or low frequency, that is our bass frequencies. That's low pitch, that's like bass. Whereas high frequency, if it's going like up and down really fast, that high frequency is a high pitch. That's like the treble. I don't know if that's how you spell treble, but something like that. Maybe it's LE. An octave, if you've done any music in the past, an octave is when your frequency is doubled. So if you go from a common frequency in music is 440 hertz. If you go from 440 hertz up to 880 hertz, that's exactly double. That's exactly one octave then. That's how we define an octave. Volume is determined by amplitude. So here you can kind of see this is the amplitude of a wave right in here. If that amplitude increases, so here you can see the amplitude is much, much bigger, that's where that increases the volume. So that's a loud sound. So if the frequency is determining the pitch, that's like what note you're hearing, then the amplitude of the wave is determining the volume. So then here's a question for you. If I sing a note and play the same note on a guitar, you can hear a difference. So here, I grab my guitar, I'll play you a note. Okay, so here's the game. I'm going to either sing or play a note, and you tell me, is it the guitar or is it Gr11? That was Gr11. There's the guitar. How do you tell the difference? How is your ear doing that? What your ear is doing is it's sensing something other than the basic frequency, right? I'm trying to sing the exact same note that I'm playing on the guitar. Same volume, same frequency, same everything. What I can't control is the overtones. This is actually what helps you tell one person's voice from another, right? If let's say two people with the same depth of voice, let's say two guys are in the other room, both start talking, or one starts talking and then the other talks, the way that you can tell the difference between their voices, if you know them well, the way that you can tell the difference between the voices are these overtones. Overtones look something like this. Okay, the basic frequency is right here. Okay, so that determines what note I am singing, or whether I've got a low voice or a high voice and that kind of stuff. But everybody's voice has a unique set of these overtones. So as the wave goes up like this and back down, you can see there's like extra wiggles in here. And then here it's coming back down following this. So here's the low part, in here, but there's extra wiggles. Those extra wiggles are the overtones. And oftentimes we have more wiggles than just what's shown here. This is a really simplified version. But sometimes you might have, like within this, you may have extra wiggles going up and down, and then here extra wiggles going up and down. Those overtones, everybody's voice has a unique set of overtones, which is why you can tell one person's voice from another, or me and the guitar when I'm trying to play one or sing one. A pure note has no overtones. That's like a very, computer-generated sound, like just a beeping out of a computer or something like that. That beep, that's not a very nice sound. That's a pure note. In general, the human ear doesn't like that. We like rich notes, which means they have overtones. So we like things like the human voice, or instruments like a saxophone or a clarinet or something, those reed instruments, they have very rich notes. We like that as humans. Here's just a quick little graph of a violin's overtones, and you can kind of see, here is the upwards motion, here's the downwards motion, here's the upwards motion, here's the downwards motion. So you can kind of see, there's the basic note, but look at all the extra little wiggles. It was very like jagged going up and down like this. And again, it doesn't look very nice maybe on a graph, but the human ear likes that. And that's it.